LU factorization works most of the time, and it's great. It's nice, it's compact. However, there are some instances where LU factorization will not work when we cannot just do elimination steps, when we actually need to do what's called row swaps or pivoting, where essentially we can use row swapping in order to get rid of an instance where we might have 0 in the pivot location. Because a 0 in the pivot location means we can't do our elimination step. So an alternative to LU factorization is PLU factorization, where we're going to do what's called partial pivoting to ensure that the largest magnitude, so we're looking at absolute value, entry is located in the pivot location prior to doing our elimination steps. This is going to overcome the problem when we have zeros in the pivot locations, and this is going to give us a situation where our L matrix is going to have the smallest magnitude values. So we're going to run into fractions more often using partial pivoting. What this does is, instead of it just being LU factorization, we now have this P that also shows up, which is a permutation matrix where we do row swaps. So same idea with LU factorization as is with PLU factorization. We're going to end up with 5 different row operations now for a 3x3 matrix, but it's the same ones every time. So we are going to first use partial pivoting. So we're going to swap so that we get the largest magnitude value in the 1, 1 location, in our row 1 pivot location. Once we have that, then we're going to put our 0 in the 2, 1 location by doing that same row operation we did for LU. Then we get a 0 here, using the same row operation we did for LU. Then in column 2, we're going to repeat the process. We're going to pivot. We are going to swap until we get the largest magnitude value in the 2, 2 location. However, when we talk about column 2, we're essentially ignoring column 1 now. We're only looking at the numbers below row 1. So I put the largest number in the 2, 2 location, and then I do my elimination step in order to get a 0 in my last location for a 3x3. We would continue this process algorithmically for anything bigger. Whatever we end up with is going to be U. This is U. P is going to be my permutation matrix from my first row swap and my second row swap multiplied by each other. Technically, it's their inverses, but the inverse of a permutation matrix is the matrix itself. And then L is a little bit more complicated now. L is more complicated because we essentially need to construct L by working our way back up through the row operations. So L is first constructed. It starts out like it did before. We're going to put in L32 or negative L32. And then what we do is we're going to do the same row operations we did for P2 on our L. So we're going to do some row swaps. So maybe we swap 1 and 3. Actually, we maybe swap, that wouldn't work, no, 1 and 3. We might swap 2 and 3. We might. Depends on what we did for the step D. Sometimes our permutation looks like identity. Once we do that row swap, if we need to, then we're going to put in negative 3, 1 in the location and negative 2, 1 in the location. And then our last step is to do our row swap again. So maybe we swap row 1 and 2. And we will see examples of this, but essentially we're going to work our way backwards. That's going to be our L. L is not going to end up as a strict triangle matrix anymore. It might end up looking something like this. It might end looking something like this. If we want to get L back into its strict triangle matrix form, we would just multiply it by P. So it turns out that PA equals PLU. A lot of times you'll see these two combined. A lot of times you'll just see it as LU. You might see in your homework that way. That just means that P is multiplied by L in order to make sure it's in a strict triangle matrix form, to make sure we have those zeros in our triangle. And so if you ever see PA equals LU, it means that the P is multiplied by L, so that's in a strict triangle matrix form. But if we say that PA equals PLU, then we can use it to solve our system equations the same way we did with LU factorization. PAX equals B, PB. If we multiply A by P, we need to multiply B by P. So it shows up twice. Or PLUX equals PB. Once again, we can say that UX equals Y. So we separate it out, PLY equals PB. Turns out that if L is not combined, so if this is combined, if we have LY equals PB, then we have to multiply P times B, which essentially just rearranges B into the corresponding, the correct rows. But if we do have L separated, if it is PLY equals PB, then we don't even need to do that multiplication anymore. It doesn't matter. But either way, we can solve for Y. Once we have Y, we can solve for X by saying UY equals X. And here's our 3 steps. And we can solve our system equations. So we will go over examples of this as well.